Okay, so now, so I hope you see it. Yeah, so I'm moving to another topic. Okay, so from the ones that you heard today, and of course also the ones that I've been discussing over the past 3 days in these last 2 weeks, because I was talking all the time about fermions. I was talking about all the time about baryons, and especially those with strangeness. But now the idea is also talk to you a bit about the physics of strange mesons, okay? Because apart from baryons, we also have mesons that can carry strangeness. And actually, this is also a very interesting field, a quite active field. Mainly, it is really mainly correlated also with experiments and a bit of neutron stars, okay? But I think, for example, my point of view, of course, is that while hyperons are really, I mean, we have experiments and there is also a strong connection with neutron stars. Kaon's, this connection it is, but it's not so many people and scientists focusing on that, and I will tell you exactly why there is more interest probably in baryons in neutron stars than strange mesons. So these are the different scenarios, these pictures, nice pictures here that I took, from the internet actually. Well, I made some of them, but still, so, there is experiments actually on that they are called Chaonic atoms. I will mention them a bit. So basically, I will say, that an electron is substituted by a K-, and therefore the features of those atoms changed. There's also, especially since the beginning of this century, it was a really interesting possible scenario of having anti-Keon nucleon bound states in nuclei. So basically having some studying free body interactions between an anti-Keon and a nucleon belonging to a nuclei. I also heavy ion collisions, and is also an interesting field that people have discussed, strange mesons. And finally, there is an interest as well in neutron stars, but as I said, maybe there hasn't been so much development in that direction, which is the possibility of having kaons inside of neutron stars. And then I will tell you the conditions, and then I will show you what people have been doing here. So what are these strange mesons? You saw in the pictures I was putting this case. So I'm talking about anti-kaons, which are those ones, and kaons, okay? So basically, an anti-kaon or kaon is a meson containing one strange or anti-strange quark. Indeed, the anti-one are the ones that are containing a strange quark, okay? Whereas the kaon one are the ones which are containing the anti-strange one. And actually, the works, I mean, I've been focused on both of them, kaons and anti-kaons, but a lot of attention has been done in the antiparticle, in the anti-kaon. Why is that? Because of the content in strangeness, because of having a strange quark. So basically, the interaction, you can see here, this is the kaons, so you have this anti-strange and then an up and down, okay? Whether the anti-kaons are the ones that carry strangeness, okay? And the thing here is basically, if you think, these anti-kaons interacting with nucleons, okay, with neutrons or protons that made with up, down, and strange, so you already can see, thinking in the quark picture, that there could be a strong annihilation of this D bar or U bar with the up or down quark belonging to one of nucleon. And therefore, actually, it is seen that the interaction of anti-kaons with nucleons is stronger than the case of the kaons, which this annihilation is not present, okay? Well, you know as well that those are lying in this octet of mesons. So together they are with the pions, okay, with the strangeness 0. So you have here for a strange +1 the kaons, and then for the K- and K bar 0, which are the ones that are called anti-kaons, are sitting here with the strangeness -1. Okay. So as I said, where to find them, and this is what I will discuss probably in the second hour, like different scenarios where people have studied these anti-kaons. So as I said, neutron stars, but also experiments here. Here I mean on Earth. So I'm talking about heavy ion collisions. Heavy ion collisions, for those who doesn't know, is two nuclei, heavy nuclei colliding. And then in the process, after collision, they generate, depending on the energy, they could create this quark gluon plasma, and then this hadronizes, and at the end you have again hadrons. But then you create this dense medium, and then the properties of the different particles created in this dense medium change. And this is also in a scenario where to study strangeness, and in particularly kaons. And then you have atoms with kaons, and also bound state in nuclei of kaons. Okay, but this I will, but just, this is just to show you the importance of these strange mesons, and something that I will discuss more into detail in the second hour of this lecture. So this is the outline of the talk. So basically, I'm going to introduce you the anti-Keon nucleon interaction, and I'm showing you now this quark bit, this small diagram, and why is so important this interaction. And in particular, I'm going to discuss one state, which is the lambda 1405, which has actually the quantum numbers of this anti-Keon nucleon, okay? And then actually, the behavior of this interaction strongly depends on the behavior of this resonance. So it's kind of an interplay and a feedback between the resonance and the interaction, okay? And then I will come to bound state, to this anti-Keon nucleon bound state. So I will show you very briefly, but that you have an idea of the experiments that have been done and the theory that has been trying to explain what experimentalists were finding, and also predicting before experiments were analyzing the data. And then in order just to move to neutron stars and to move to heavy ions, for example, we need the interaction of anti-kaons with many other particles, in particular, many other nucleons. And then finally, in the last hour, as I said, I will discuss a bit of experiments and observations. So from atoms, we will move to stars. So this is kind of a short summary of what people have been doing in the anti-Keon nucleon interactions in actually the 50s of the last century, okay? So the anti-Keon nucleon interaction, actually, if you look at the anti-kaons, okay, which are again shown here, and now now we look at this diagram, this quark diagram with the quark structure of these particles. So you have the anti-Keon interacting, for example, with a proton. You can see, that that there is this possible annihilation of the anti-up quark with the up quark of the proton. And then in order to finally create an anti-Keon proton, because this is the scattering we are analyzing, then it has to be created again, this anti-up and up quark. And in between, you have something which has the quantum numbers of the strange up and down. Actually, this is this lambda 1405. Okay, so this, if you look in the PDG, you will actually see a state. We will discuss the nature of this state, but you will see some resonance, some structure that you find around 1405. And this, as you know, the lambdas are in the isospin 0, has an isospin 0. So basically, what I'm saying is the anti-Keon scattering in the isospin 0 channel is governed by this presence of this state. What is also plotted here in the sense that if you calculate the threshold of production of the anti-Keon nucleon, summing the masses, basically is this threshold, you will see that this lambda 1405 is lying 27 MeVs below this threshold, okay? So there is some state that is very close to the anti-Keon nucleon threshold, and therefore the scattering will be dominated by this presence of this state, which is actually located below in energy. So it's a subthreshold resonance, but it has some effects actually at the threshold of the anti-Keon nucleon, basically because of the width, right? So, but this idea now of this resonance actually was already proposed, in the 50s by Dalitz and Tuan. And actually, it as a molecular state, okay, as a state made of a meson and barium molecule, okay. And actually, the study of this state was pushed in the 90s, in particular because of being revived because of the use of unitarized theories. So I mentioned already this Bruckner-Hartree-Fock right, yesterday. So these theories that that have this multiple scattering, unitarize, well, means, there are this multiple scattering means that, probabilities are conserved. So basically these theories, but using Meson exchange models that they were in the 80s, right? Well, even before, but from the anti-Keon Nucleon, you will see that even in the late 80s, in the 90s, actually, beginning of the 90s. And also because of the interest also on effective field theories that incorporating the strange degree of freedom and caring now about Meson and baryon with strangeness. So here there's a list of people who have worked different models on these Meson exchange models since the 90s. And maybe you see even more with the chiral effective field theory with the chiral Lagrangian. So I'm going now to show you a bit the ideas and what I'm discussing about these Meson exchange models and the chiral effective Lagrangian, because actually I already told you about that in the context, right, of baryon. But actually, those scientists working on baryon, actually, they also work on Meson and Meson baryon. Okay, and the idea was also, to have this exchange of bosons, trying to explain not only the interaction of nucleon-nucleon, but also, as we discussed, of hyperon-nucleon, but even without baryons, about the pion-nucleon, and also from pion-nucleon moving to, for example, anti-Keon Nucleon, and even pion-pion. So what I'm saying is that, of course, you can also start to try to understand the interaction of not only baryons with baryons, but with mesons and baryons within this boson exchange model. Okay. And one of the models used for the created for the anti-Keon Nucleon was coming from the Eulek group. That actually this gentleman already worked on pion-nucleon and then put, the strange degree of freedom of strangeness, and therefore also work on the anti-Keon Nucleon. Okay, and here you have the diagrams actually that this Eulek Meson exchange model is containing. I'm not giving you the details on how they are computed, but I mean, you have the main idea again that you have two particles interacting with the exchange of a meson. And this is these first orders here, for example, anti-Keon Nucleon going to an anti-Keon Nucleon, and then you have the exchange of the rho, omega, and sigma. But actually, not only this, but also for the anti-Keon Nucleon, you can have what they are called, they did not stop as at the level of only one meson exchange, but also, here you have what is called a baryon exchange, a pole diagram. And even exchanges of more mesons that, as I was indicating as well in the nucleon, that, okay, you can explain the features of the nucleon, but if you want to refine your theory, you better, or all these people, all these scientists were also working on having higher order corrections. Okay, so like, for example, exchange of two mesons, and they are called box diagram with different intermediate states as the anti-Keon and nucleon. Okay, this, as you can see, is starting from an anti-Keon nucleon going to an anti-Keon nucleon. But of course, as I was also mentioning for the hyperon nucleon, you have to take into account all mesons and baryon with the same quantum numbers. So basically, you have to think of some state of some two-particle state, which is a meson and a baryon. So basically, that has also baryon content, and that has a strangeness -1. And this is the case, for example, you can see here of the lambda pion or the sigma pion, which also have the same strangeness and quantum numbers as the anti-Keon nucleon. And of course, if you have these pions and lambdas or pions and sigma in the final states, you can also have the crossing term. I mean, crossing terms, I mean, not starting with anti-Keon nucleon, I mean pion lambda going to pion sigma, or pi sigma going to pi sigma. So this is also incorporated in this Eulek Meson exchange model as the initial interaction. And from that on, you do unitarization and you get your observables. From the point of view of the chiral Lagrangian, we discussed baryon-baryon. I show you a bit, the main features of this baryon-baryon. This is the chiral Lagrangian for meson baryon, okay? So basically, this is the effective theory, the Lagrangian, for the leading order and the next to leading order. The leading order looks like that. So how do you understand this? So you have here the B and the B bar as the baryons, right? And then you have the interaction through baryons mediated by this d mu. This d mu is actually the covariant derivative, which includes, if you see it here, what is called a functional, which is this gamma mu that incorporates in this through these U fields the phi matrix, which contains the mesons, okay, the pseudoscalar mesons, okay. This is where the coupling of the phi mess of the pseudoscalar mesons like Keons appear to the baryons, okay. So this is why it will be interesting for us if we want an interaction of a Keon with, or an anti-Keon, here I just show in general K, with the nucleons, for example, okay. Then we also have a term that breaks explicitly for the baryons, the chiral symmetry. And then you have other two terms actually that also give you some interaction of the pseudoscalar mesons with the baryons, okay? This is the leading order, and now I will connect it with these diagrams here. And then you have a next to leading order, which in this power counting of this low energy scale of the mass, I'm talking here of the mass of the Keons with respect to the mass of the vector mesons, like around 1 GeV. Then you have some extra terms. And as you can see here, what it means, each of them, this chi plus is kind of a matrix element that includes, let's say, the mass matrix, okay, which actually breaks chiral symmetry explicitly and also contains, through this V0, this is the order parameter of the chiral restoration, the spontaneously breaking. This is the condensate, the quark condensate, okay? And there are different values here that are they're called coupling constants that are, or next to leading low energy constants that are not determined and need some experiment to be fixed, okay? So how is its correlation with these different diagrams? So actually, through this first term that I was mentioning of the coupling of the baryons through this D covariant derivative that contains these U's, which at the same time are exponentials of these 5 fields, which are the Meson fields, is where it's coming the interaction or the main contribution of the interaction between mesons and baryons, which is indicated here. A meson interacting with a baryon and a meson interacting with a baryon. So actually here in the low energy limit, this reduces with the well-known Weinberg-Tomozawa interaction, okay? Then from the leading order, there are also some extra terms which correlate, you know, a baryon with a meson and a baryon. This is what you see here, a baryon. Here you will see a meson, and here you see another baryon exiting. That gives you this vertex here, okay? And this is helped to understand the interaction mediated by what they are called Born contributions, or the exchange of some baryons in this interaction, okay? Similarly, you can see going back this kind of diagrams here, okay? And then the next to leading order actually provides you with some extra derivative terms that are corrections to those other terms. In fact, as I was saying here, I mean, you can see that the most important contribution in almost all channels, because some of them, this contribution is 0 because of the symmetries, but in most of them, in particular for the anti-Keon nucleon, this is the most important contribution. Whether the Born terms and next to leading order contributions coming from these diagrams are needed to a fine-tuning of the results, which is also important if you want to go further and also move to larger energies, okay? Because this is important when we are close to the threshold of production of anti-Keon nucleon, but as you increase in energy, this next to leading order corrections become important. In particular, it's important to something that people have been working also in experiment, which is the Chaonic Hydrogen, okay, where you have a Keon linked to hydrogen, as the name indicates, and in particular to the shift and width of the 1s state. So, but before going to that, just to show you again the connection, okay, between our theory, which comes through the scattering amplitude, okay, which is the part that it indicates all the scattering processes that is into, by this formula into the S matrix of collision operator, and how this scattering length is correlated with the scattering length and also the cross sections. Okay, I already showed you a bit this before, so I don't think it's a problem here. So this is the Liebmann-Schwinger equation, okay, for the scattering amplitude. And why I wanted to show that is because, for example, for the shift and width of the one state, you can link its energy, okay, and its width to the scattering length, which is this A here, okay, which actually theory can provide you. I will come back to this formula, but just to indicate you that, there was some previous experiments, previous to the development of the next to leading order, by Keck and Deer, so also two collaborations, the Keck in Japan and the Deer in Italy. And if you look at this diagram of width and shift in energy, you see that they were kind of incompatible, okay? Somehow, well, there is a big error, okay, because this is kind of the values between what, 60, 150 and 180, 90 for the width, whether the shift in energy was, also pretty big. But Deer had, smaller, let's say, errors, but still they will not be compatible one experiment with the other. So it was this Siddhartha experiment at Daphne here in Italy, where it seemed, to this, or to clarify the discrepancies between these two experiments, having, better resolution regarding the width and the energy shift, okay? And with this, actually, these results have helped also to constrain the next to leading order, okay, to constrain all these constants that we were lacking of, okay? So somehow there's also a feedback, okay, between theory and experiment, which is expected. And in particular, you see here, this is amplitudes, subthreshold amplitudes. So here you will have the threshold for anti-Keon nucleon. This is the mass, the sum of the mass of the two particles. And this is the real part and the imaginary part. So this is kind of an extrapolation using the best fit with these Siddhartha results through, using probably this called desert type formula, where you relate the width and the shift with the scattering lengths, okay? And these are the results of this Siddhartha. I'm just showing, as I said, some best fit, theoretical best fit using this data, okay? Of course, we are talking about scattering data, so it's a threshold, okay? But this is already sub-threshold. So this is something that definitely needs to be, tested somehow experimentally, but right now we are still in here, okay? We hope, for example, with deuteron or some other experiments involving deuterons and kaons, that somehow this, we will have access this sub-threshold region. Okay, this is just to show you a bit the connection with these effective theories, with experiment, what people are doing. I said the lambda 1405 is a state, but actually it's not one state, okay? In fact, this was kind of a, a prediction of the theory, the fact that actually we have two states that are superimposed, and you only see, if you analyze the energy axis, which is the real axis, the one that experiments have access, you will see only one state. But actually, by having some specific reactions to pin down the properties of each of these resonance states, you see actually these two double structures. So, as I said, actually this was a prediction of the theory, doing some theoretical calculation and finding that we have two poles that, are coupled or are generated as a molecular state, mainly because on one hand, one of them, mainly because of the interaction of pions and sigma, whether the second one because of the interaction with antichaons and nucleons. And here you have 4 groups, well, actually 3, and the predictions for these 2 resonance states. So basically there is one resonance lying at energies close to the threshold, a bit below, okay? The threshold of antichaon nucleon is 1,435 MeV. So you see lying almost on top of this antichaon nucleon threshold. And a second pole, lower in energy and wider, okay? So actually the one that it was lying on top of the antichaon nucleon threshold is the one that has the most important molecular component of this antichaon nucleon, while the other one comes from the pion sigma. And here I'm showing histogram, right, of the invariant mass versus of the mass, where you can see actually the 2 reactions. This is a Keon induced and this is a pion induced reactions, which were, were effective, let's say, in finding, the 2 poles of the lambda 1405. Okay. So this is the situation with the double pole structure. And because of the importance of this lambda 1405 or this 2 lambda 1405, I mean, you will see nowadays, this is from the PGV, that is mainly belief, there is still people thinking there is only one state, but I think the community is already 90% of the scientists agreeing that there are actually 2 states. And people, of course, have tried, to pin down the structure, the shape of this state, because at the end of the day, the shape of this state is the one that is giving you this real and imaginary part. Okay, somebody raised her hand or his hand, Adriel.
Yeah.
Yes, hey, yeah.
Why is the imaginary part so large? Of the pole?
You have to imagine that if you have, imagine that you have a function, okay? 1 divided by x, okay, or 1 divided by x minus some constant, okay? So you have a pole, okay? So when you have a pole, right, and mathematically, okay, I'm just telling you, then you will have what? A delta function. The imaginary part will be a delta function, right? I mean, when the x is equal to x0 or the a, you will have, okay? This is mathematically what you will find if you have a pole in an amplitude, okay? And this is what you see. Now, physically, it means that there are decay possibilities. When you have imaginary part and it's so large, it means that the probability of decaying of this is very important, okay? So somehow you have decay channels, and actually this means that this can decay, this lambda 1405 mainly decays on pion sigma, which is lying somewhere here, okay? So let's say when you have, like, also the delta, have you ever thought why the delta is so wide? Because of the decay into pion nucleon, right? So the delta is in the PDG, and then this is what you will observe, some bright Wigner shape, okay? And this is the same for the lambda 1405. Does this answer your question?
Yeah, thank you.
Okay. And because of having this structure, this shape of which is like a delta function but smeared, okay, with some width, then you will have this shape, okay, this going down and up, so change in sign, okay. And this is, you also see when you have a delta function, then you also see the real part, okay, is kind of diverging, going to infinity on one side and to minus infinity on the other side, okay. So this is the shape mathematically you will find, and the meaning of this width, as I said, is because of decay. Okay, now, as I said, because of that, there has been a lot of progress and a lot of experimental work trying to find this resonance in different reactions, okay? I mentioned Keon-induced reactions and pion-induced, and actually the Keon-induced is more sensitive to the high energy pole, whether the pion one is to the low energy pole. This is what you saw here. This is the Keon-induced So it's shifted with respect to the pion induced. So it means that it's more sensitive to this high energy pole than to the lower one, which is more sensitive to the pion induced. But there's also a lot of work on photoproduction, okay? Photoproduction, for example, you have this reaction photon in nuclei, so photon going to a proton, generating this lambda 1405 and a kaon, and then analyzing the invariant mass of this pion sigma, which is where it decays to see this lambda 1405. And this is an example for different energy reactions. And you see, actually, there are three sigma pi. So you have sigma 0, pi 0, sigma plus, pi minus, sigma minus, pi plus. So these are the three different shapes. And the experiments are those with the error bars, and the theory is those lines here. Okay, this is an example. And this is for photon induced. But there's also kaon induced in deuteron. Okay, this kind of reaction here, and an antikaon going to deuteron. And there's also in proton-proton collision. So proton-proton generating a proton, and then a kaon and a lambda 1405. Okay, so there's been a lot of experimental work in that direction. And of course, the theory follows, or at the opposite, right? So theory sometimes predicts something, and then theory and experiment come and checks whether this theory is you know, you can understand the experiment using that theory, that's model. Okay, this is just for the anti-Keon nucleon. But now I told you that one interesting scenario that actually started in the beginning of the century is the possibility of having this anti-Keon nucleon bound state. So the fact that having this lambda 1405, this molecular state, it means as a Meson baryon molecule, it means that there is some attraction, right, on the Meson baryon molecule. I mean, they're in between the Meson and the baryon. Otherwise, you will not have anything bound, okay? And the fact that this is attractive and generates this state gives us the thought of maybe if you have more nucleons, we might have clusters of antikeons with nucleons. Okay, and actually this is this state, the antikeon nucleon, that theoretically it has been studied in a lot of detail. And as an example, here you have the width of this state as a function of the binding energy, and different models and different way of finding this few body system. Okay, of course, actually I believe it was one of the first Akeishi and Yamazaki, although the model, let me tell you, it was very simplistic and not very, my opinion, okay, not the best one you can use for the antikeon nucleon, but still, I mean, this push, the experimentalists to look at this state and whether they could be found. And there was, initial claims by Finuda, Disto, and Obelix. So you find here these experimental results that actually some of these claims could find some interpretations in terms of final state interactions, or could not be reproduced later on, okay? Now, more recent experiments in J. Park or in Amadeus, did not find any signal, or if it was found, like in the case of the J. Park E7827, may also have not the interpretation of this bound state, but of a sigma, it would be a sigma star nucleon state. Okay, so this also is under debate. And one of the latest one, the J. Park A15, which is now indicated here, found this structure close to threshold, and it seems, there is being corroborated with some theory like this group, Sekihara and collaborators. So actually what I want to point out here is, again, the interest on this interaction and the fact that you could find an antikeon nuclear cluster, okay, antikeon with two nucleons. And this triggered the interest whether, you could really find experimentally those states. But, on the one hand, theory, it has a lot of ambiguities and a lot of uncertainties. And also it seems that some of these experiments could also be explained not by this state, but some other more conventional, let's say, explanations. So I'm showing you the different groups that had been working on this theoretically, okay, on this antikeon, actually proton-proton state. And if you look at them, I mean, this is the list, you see binding energies actually ranging from what? From 9 to 95 MeV. And width, if you take the limits, it will be between 16 and 110 MeVs, okay? So basically you see a variety of results theoretically. You also saw them here, okay, in this band here, which now you, in this other plot, you also see them with more recent analysis, okay? So there's a lot of variety in the width and in the binding energy. And this is because of several reasons. Well, the first of all is that we are talking about a state, you know, which results from this subthreshold extrapolation of the anti-Keon nucleon interaction, okay? So we have a bit of control with scattering, okay, and also with this Chaonic hydrogen, this state close to threshold. But if we go sub-threshold, there is a lot of extrapolation in those methods, okay, and in these different models. So therefore, there is this variety of binding energies, okay, because these models, you could divide them between chiral models, okay, based on this chiral effective Lagrangian, or more phenomenological models which use some density dependent interactions. So basically, it's a bit the same as you see, you know, in hyperon nucleon, that you have phenomenological models and ab initio models. And between these ab initio models, the chiral model is the dominant one in the past years. And there is a difference actually, because if you analyze the phenomenological versus the chiral models, the chiral interaction usually gives lower binding energy, so less attraction than in the phenomenological ones. And if this interaction is less attractive in the chiral models, it means that the binding energies of this three-body system, okay, it will be less. Also, the way of building this few-body system, okay, because actually for doing this, there are different methods. There are Faddeev calculations of three-body. There is also variational methods. And there is a more recent, which is called coupled channel complex scaling method. So there is a different ways of dealing with the three bodies. And it also has its uncertainties in the way of dealing these calculations, because they make some approximations that in some case that it will give you some errors, okay? Variational methods take into account cannot take into account, the full three-body interaction, whether the Faddeev does. But on the other hand, Faddeev calculations need of separable potentials, and this is also an approximation, okay? And then this most recent, it seems that it takes, you know, this full three-body plus other beyond two-body interactions, but this is also at cost of a very high computational cost, okay? So, I mean, this is the situation. So you can see there is still not a clear answer for that. But okay, this means a lot of work has to be still done. And then maybe in the last 10 minutes, if you allow me, we will stop in 10 minutes. We'll be discussing anti-Keons and Keons in matter. Okay, so I will start with Keon Nucleon. And Keon Nucleon, as I said, it's not so strong the interaction, because mainly you could see at the quark level, because they have this anti-strange quark and then the up or down quark, and this cannot be, let's say, annihilated with an up and down. I mean, you don't have this annihilation as you have when you have anti-Keons. And therefore, this means that you can make some low density approximation when you try to compute the interaction with the medium, because now we are in a medium, okay? As before we were with a hyperon in a full many-body, with lots of nucleons. Here you have a meson with lots of nucleons, okay? And in this approximation, the important thing was then to calculate the free scattering, okay, of anti-Keon nucleon going to anti-Keon nucleon. So there has been different ways of doing it. These three ones will be like more like phenomenological models, and these will be more ab initio, in the sense that this one takes into account free interaction and do the unitarization, while these ones, you know, already are models in a many-body system, okay, that use some kind of functionals and so on. But in any case, it is more or less clear that there is a repulsion, okay? So Keons with nucleons feel a repulsion, okay? And more or less all of them agrees. And this is by the fact that this interaction, it's not so strong, and in the case of the anti-Keon nucleon. So the anti-Keon nucleon, there's also been these phenomenological approaches, relativistic mean field or phenomenological models. And actually, there is a discrepancy on the how deep, how attractive the interaction is. This is, for example, using Meson, as I said, relativistic mean field, where this one is kind of the density dependent that is fitted to experiments, in particular Chaonic atoms, okay? And if you compare these two, you would say, yeah, we observe, for example, a minus 200, I was putting it here, between minus 100 to 200 MeV at saturation. Here at saturation, you will have like minus 100 MeV, so this is pretty large, this attraction. But there is some, for example, on that one I will mention later, there is a problem here because you're analyzing chaotic atoms and you're doing some density dependent in order to fit data. This we will see in the next hour. And this data is chaonic atoms. I'm talking about atoms. So these chaons are in the orbital stage. So they don't feel the center of the nucleus, okay? And these extrapolations look at the center of the nucleus, okay? So then you have to be careful on how you extrapolate this data to understand what is happening inside. I will mention that a bit later. And of course, you can do this unitarization now with these chiral models or Meson exchange models. So here I'm just showing you a type of Bruckner-Hartree Fock that I discussed yesterday. So it's just this effective interaction in matter where you have the propagator changing matter. And the idea is that you have this propagator here, which is dressing matter, includes these self-energy corrections, and which in order to calculate them, you need the effective interaction, and therefore you plug it in here, but then you get your effective interaction, and then you get again the effective interaction, and you get your self-energy. So this is again, I mean, as I said, it's a Bruckner type equation that you have to solve, but in this case for mesons and baryons. Okay. And what is the effect here of this process in matter? So you have the Pauli blocking because you have baryons. Okay, before you had two baryons in the intermediate states. Now you have only one, and of course this self-consistent process. And this is how the amplitudes look like as you increase, the complexity of the many-body framework. So let's look at this continuous line here. I mean, dotted line. This is the what we were seeing, okay, before this amplitude. This is the minus real part, and this is minus imaginary part, okay? So you see here maybe better this resonance, okay? The threshold is here, and then connected to that there is this shape here, okay, going down, up, and then down. This is minus real part, okay? And the threshold, which is a 1435 MeV, it's somewhere here, okay? So the effect of Pauli blocking is making most difficult to generate that resonance because you are blocking states now, okay, as comparing free space. So this has an effect of moving the resonance to higher energies. So you're moving it to higher energies. And this is important because this is where the attractive character analyzed theoretically comes, because before, around threshold, it's here and it's minus, okay? So I'm having positive values of my real part. This was around threshold in free scattering. But as you put a medium, and because of this Pauli blocking, now if you analyze this region here, you are moving to attraction. So now you have positive values, but this is the negative, so it is negative, and you're getting attraction now. So medium makes attraction, okay? Provokes you, this Pauli creates this attraction, okay? But this attraction is probably not so big as this amplitude might indicate because of the self-consistency, because self-consistency means, as I said, doing this analysis again, back and forth. Once you need the self-energy, you need your effective interaction, but to calculate the effective interaction, you need the self-energy. And this back and forth actually smoothens, okay, the amplitude. It's here now, okay? This smoothening is because this is opening, because now your thresholds are not so clear anymore, because now you have energies, you have imaginary parts, and somehow this means that you have more decay channels inside a medium. So before you only had the scattering, but now because of having many nucleons, you have many new decays that were not present in free space. And this makes your amplitude, your imaginary part bigger, so it's spread over energies, and this also correlates then through dispersion relations through the real part. And this is a self-consistency, and of course, this also, if you have pions, you also introduce the medium corrections, and well, things get smoother, but still, you have the smoothening. This is what matters. And this is the amplitudes. These are the amplitudes in matter that then later on you have to somehow analyze. And this is the difficult part, okay? And actually, well, this is the theory. This is, you can forget. I mean, this is what I was saying. And one quantity that people look at is correlated with the self-energy, which is the spectral function. The spectral function is a theoretical object, okay? So the correlation with experiments, you basically correlate it with the amplitude, with the imaginary and the real part of the amplitude, okay? But this information, it's here. The spectral function is kind of a probability of finding a particle in a certain energy. So it's like, okay, if you have something which is stable, let's imagine, okay, the Keon or the pion under strong interactions, okay? You will have a delta function centered at the mass, okay? This is a stable particle, okay? But if you have, for example, a delta, you know that it has some shape, okay? It has some Bright-Wigner distribution. And this is because of the possibility of having decays into, for example, pions and nucleon, right? So in medium, this Keon is not a stable particle, okay? In medium, this particle develops an amplitude. And this is the probability, let's say, of finding this Keon at this energy. So the main probability, this word probability is like to saying where you will find, what is a Keon in a medium. So a Keon in a medium has some shape in the sense that it tells you that you probably mostly find it around the mass, but you can consider also, okay, on something which is lower energy, like for example at 100 MeV. So there is some strength there, okay? So it's like thinking of the delta, okay? But here the decays are because there is a medium. And the interesting thing here is, well, I didn't say, this is the spectral function at some density as a function of the energy. This, I guess you understood, for different temperatures. Okay, these are different temperatures. And the interesting thing here is that this, you would say, okay, this is like the kind of a Bright-Wigner, but actually it is not. It could be more complicated. And this is another density, and it has some bumps and has some, this right tail is going faster than this left tail. And this is because there are some excitations that appear in medium that has the same quantum numbers. So this faster going here actually is given by the presence of this lambda 1405 hold. So basically, if you take the lambda 1405 and subtract the mass of the nucleon, you will have some strength close to that value here, okay? So my idea here is that a Keon, what is a Keon in a medium? Well, a Keon in a medium is not something clear. It is, like some probability, okay, of finding this because of the interaction with the medium. Experimentally, of course, this is not seen. I mean, this is not seen. You basically can maybe, try to find real part how the mass of this particle is changed, and this is given by this maximum in your spectral function. Okay, this is how this mass will be shifted in this case with temperature, and also the half height. I mean the width of this the function at half height is giving you the imaginary part, okay? And this is something that you might be able to test somehow in experiment, okay? So this is for that, and I think, yeah, I'm stopping, as I said, here. And we can, of course, ask questions. I mean, especially if this theoretical object, that what a Keon is in the matter. But I always make this analysis with the delta. baryon, okay, is also something which has some width and we have some mass. So this is kind of a similar object, but the medium makes these objects unstable because it allows to decay in channels that they were not in free space. So maybe any questions?
Apparently, no?
No, seems people are tired.
Oh, well,
So anyway, we can make a break and then I will take maybe more interesting, experiments and how things look from the theory point of view. Okay.
okay. So how many minutes do you need? Are you
I mean, I don't have so many slides afterwards because you also told me like to have 15 minutes, right? So
yes,
we can make like 10 minutes if you want. And we start
yes.
at 5:15.
Yes, quarter past.
A quarter past, yes.
Great. Thank you, Laura.
So let's put this in full screen.
Okay.
Okay. So yeah, I think in the last half an hour, this is not going to take longer. I would like, to discuss a bit of, okay, this fancy, if you want, behavior of chaos in matter, which is not fancy. It's basically telling us, that they develop a shift in mass, they develop a width because of interactions with matter, how this can be tested and what predictions, okay, we can give and how it compares also with experiments that are already being done, okay? We discussed before about, or I discussed about anti-Keon nucleon bound states, and you saw that there's still a lot of discrepancies, theoretically, the ways of doing it, the results are very different, and this depends because of this subthreshold interaction for understanding, what's happening below the anti-Keon nucleon, this lambda 1405, the behavior of this lambda 1405. Also because the method used, that there are some approximation, and this also gives you errors in your calculations. And also from the experimental point of view, there is also, discrepancies, because as you could see, there are results that are not being confirmed in some experiments, others they are. So there was also, a complicated situation in experiments. And I'm not going now to talk about this. These were few body systems, but now I'm going to talk to you about many body systems. So systems where you have few kaons, in this case, anti-kaons, I'm talking all the time, and an infinite or a huge number of nucleons, basically, okay? So this is a scenario for neutron stars, also for chaonic atoms, and also in heavy ions, okay? So let's start with chaonic atoms. So the definition of a chaonic atom is actually, I was trying to tell you before, atoms in which an electron is replaced by a negatively charged anti-kaon. So the idea is that somehow you can create them. So with with really slow anti-kaons colliding nuclei in such a way that this is bound in the orbital, in the orbits, in the atomic orbits. But of course, the anti-kaon as compared with the electron is what? An electron has half MeV, its mass, an anti-kaon is around 500 MeV. So it's like 1,000 MeV, 1,000 times more massive. And this also means that this will get closer, this orbit, will get closer to the nucleus, okay, to the core. And if this is the case, then it will see the core, at least its surface it will see, okay? And this actually is helping or giving information on the interaction with anti-kaons with the nucleons. So there were different ways of approaching and describing the data. One of them was these phenomenological models. And here is again a similar plot as the one that I showed you before by the same group. Maybe this was not older version, where you have here a nickel and then an anti-kaon in nickel. And these were phenomenological fits to the data. I will show you the data later. But the idea was, how deep this potential, this attraction is as you get to the center. And these are different chi-squares, okay? Actually, it seemed that the best chi-square was giving you attraction at the center of the nuclei of around 200, around between minus 1,500, 100 minus 150 and or between 200, minus 200, okay? How is this done? Basically, the idea is that you have a model for the interaction following the profile of the nuclei, so the density profile of the nuclei, and you solve this Schrödinger equation, okay, or Klein-Gordon equation in this case, with this potential that is given you by this phenomenological model, okay, that tells you the, following the profile of nuclei, how the Keon interaction changes. Of course, if it's a K minus, which is the case, you also have some Coulomb interaction, and the idea is to solve this, okay, and see the different states in the different nuclei, okay. In this case, this was this profile used, and it was good fitted actually with the data. This is actually the data, okay, that they have from the shift and the width as a function of the zeta number of the nuclei for the 2p, 3d, 4f states. This is the data, okay. And these results are actually not those here, not using that one, but using a model that had a less attraction in the center. This was done with the chiral model, actually, and this is what is written here. Now, if you use theoretical models that are based on this chiral interaction, that actually I was telling you it has less attraction, which has a moderate attraction, can also reproduce the chaonic atoms, okay, can reproduce well the data, okay, the width and the shift of this. And actually, this is understood, at least at the level, you know, because saying, okay, as I said, this chaonic atom is feeling the surface, but it's not really looking into the inside the core, inside the nucleus. Okay, so if you start doing extrapolations with good chi-squares, you can have lots of good extrapolations, in fact. And this actually was seen later by the group analyzing different chiral models. There's also phenomenological models. So doing a reanalysis on this, using this chirally motivated, these coupled channel, well, unitarized models, they could actually find that this is what is called single nuclear absorption in chaonic atoms. So the data is in between these two bars here. And these lines, the two reds and the two darks, are done with a phenomenological model. I don't remember if it's the solid line, which is the Prague model, which is a phenomenological model. And the KM is Kyoto-Munich model. I think is the dashed lines. And then actually this is for the lower and upper states of these different nuclei. And all the two cases were giving good, you know, and results because the data was in between these two bars, okay, for this nuclear absorption fraction. So the conclusion of it was, you know, to see the real and imaginary part and see that this Km here and the phenomenological one, the Km, there's a difference because they also add some extra term phenomenological, but the idea is that the three of them at closer to smaller densities, they were very similar. Okay, they had almost the same real part. Also for the imaginary part, okay, these different three models also had for lower densities very similar behavior. And this already was a confirmation that actually we cannot extract much information on what is happening at larger densities, because what actually we are testing is lower densities. We are testing the surface, okay? And in both, and in all the cases, those at lower densities were giving similar results. So this was a bit of the conclusion. So chaonic atoms are a good source of information of the anti-Keon nuclear interaction, but at low densities, not at densities in the core, in the center of this nuclei, okay? So we need, of course, or try at least to get some information from somewhere else. And this is what people also have been trying to do in what they are called heavy ion collisions. Heavy ion collisions, what they do is not to, you know, like this is a nuclei, the chaonic atoms are nuclei, and then you hit, you know, a Keon slow, so it binds in the orbital, in the atomic levels. But in this case, you have two heavy nucleus, gold, lead, nickel, depends on the reaction. And you collide them with high energy, which is actually ranging from energies close to the production of the kaons, so energies of 1 to 2 GeV per nucleus, or even larger, okay? And the idea of all of this is actually to explore what is called the Qcd Phase Diagram. The Qcd Phase Diagram is here, it's plotted, it's one of them that you can find in the literature. So the idea is that you plot the temperature versus the density of the chemical potential of baryons. And you try to, through different reactions, these are the different reactions. So this is when the explosion happens and then how it goes down, okay, as it goes, in order to explore how how is the diagram, how is our world? So we are sitting somewhere here, nuclear matter, sorry, here. And then it is, postulated that we might have a deconfined world at larger temperatures and larger densities, where we have this quark-gluon plasma. So the idea actually of these heavy ions is to study how this transition happens from our world we have right now to a world that is made of quarks and gluon, or even at the conditions that we have in the early universe, so at larger temperatures and low baryonic densities, okay? So this is the motivation actually to understand this matter in different extreme conditions. And one of the topics is also analyzing strangeness, the role of strangeness into this game, whether they can serve as probes for this Qcd phase diagram in the sense that they are produced, and once they are produced, they contain the information of this dense medium, and then you get and once you observe these particles and how they are changed in matter, you can understand what was the medium and they were created. This is one of actually the goals of these heavy ion collisions. So, as I said, there is a major research domain at GSI, also LHC and RIC, and it's also part of the future, at FAIR, which is a facility being built at GSI, but a larger collaboration, international collaboration. Then you have NICA, actually also having this interest in Russia, and BES in China, or J-Park in Japan, okay? And as I said, you can have lower energy collisions or higher energy collisions depending on the fast of the beams. And this then will tell you in which region you're exploring, because the more energetic, the larger temperatures you create, but the less baryonic density you have, because it doesn't have time to create baryons. So or they create a lot of baryons and antibaryons. So basically, you have less dense matter, okay? And this is what you see here, LHC or RIC, okay? And the GSI is low energy, so we are going here, and the future FAIR experiments will be here, okay? But with these experiments, you can then test, as I said, particles with strangeness. And if you study these particles and what are the conditions they were created, then you get an information on the matter at that stage, okay, that it was this particle created. So you have here the different collaborations, for example, at lower energies, CAOS, FOPI, ADES, the high energy of STAR, ALICE, okay, at RIC in the States, in Brookhaven National Lab, or LHC at CERN. And of course, the future in the sense that there will be more facilities and more experiments in that direction. So in particular, for the kaons, this is what I'm interested. There was, recent, not so recent, from the beginning of the century, results already giving us information or validating our theories, okay? So on one hand, kaons actually is here. Kaons have some repulsive character, while K- seem to have an attraction, okay? There was also some interesting issues in the fact of the kaon plus as a probe for the equation of state. What does it mean that? So when these kaons are created, they are created in a dense medium, even maybe quark-gluon plasma, okay? And then let's say you create a quark-gluon plasma and then you start hadronizing, okay? And then those particles have to propagate until you get to the detector, right? So in this propagation, K pluses, as I told you, don't interact so strongly. So they keep some information on on the time that they were created, okay, on the matter, on the characteristics of the matter when they were created. And this is why they are saying are a probe for an equation of state, because they tell you how matter at some large temperatures and large densities looks like, okay? What are the features? What are the thermodynamics, okay? So this is something that, you know, also give the interest of analyzing this kind of meson. The K minus is not, because the K minus is, I'm telling you, they interact very fast, and then they have a strong interaction with the medium, so they forget fast when they were created, the conditions, and then but they carry some other information, okay? In particular, as I said, you can get information on the interaction itself, okay, on how they propagate. And this different situation for these two will also give you, you also get information on how they were created, because kaons were created in the initial reactions of nucleon, that you will create a kaon, hyperon, and a nucleon. So this you can see looking at the masses, that it is easily to create at the beginning. But then K minuses were not at the beginning, but they actually created in secondary reactions. And this is found by analyzing the data against theoretical models that analyze the evolution on the creation and propagation of these particles. Well, these are some analyses just to put, you know, to realize the importance of these mesons. And also not only this, but also the phi meson is also contains strangeness. It's a hidden strange meson because it has SS bar. And it's also turned out maybe important, you know, the feeding of this decay channel, which it happens in free space, but also in medium, whether it was also, you know, giving information on the properties of kaons and K minuses. More recently, you know, Hades and Foppe, more recently means like 5 years ago and going on, they also studied, you know, more into what is the interaction of kaons and nucleons and antikaons and nucleons. And, you know, they found also this repulsive character of the kaon. While for the K minuses, it was difficult. To really pin down the interaction, because they interact so strongly that, you know, it was difficult to determine something, and in particularly, you know, whether the phi decay was important here. This is a very recent analysis we did. You don't have to understand it much, but just that you see, you know that there has been results trying to understand the propagation, the production and propagation of kaons and antikaons using a theoretical model, where you implement your theory, your interaction, your model on the properties of those particles in medium, and you test it again, experiments. You test it again, what they are called, for example, these are two examples. These are the B2. This is the elliptic flow. The elliptic flow is an observable that tells you how you can squeeze matter after they interact. Okay, so when you have two nuclei, okay, they interact, how the matter squeeze, how it flows. And this is this B2. And there are also, you know, was information on the production of these particles, whether it was enhanced or suppressed as respect to what is expected in free space because of the interaction. If you have attraction or you have a broadening of an imaginary part, you produce more easily these particles than if you don't. And this is what it was observed for antikaons. And well, and also as kaons, I was telling you that they prove the equation of state, but also try to set up some constraints on the equation of state of matter. Okay, this is just an example. So just to show you that if we want to go to larger densities, we have to go to heavy ion collisions, for example. And finally, kaon condensation. Kaon condensation, I think Gloria already this morning, those who were there, was explaining you a bit what it means. I mean, the idea is that you might have kaons inside neutron stars. I discussed the other day, right, about having hadrons inside neutron stars. And what were the conditions for having them, right? There was this beta stable equilibrium when you have a relation between chemical potentials. And this tells you at which densities these hyperons will appear. Because at the end, you basically have neutrons, protons, and electrons. If you think of hadronic matter, okay? If you think of quark matter, there is another issue. But if you just think of having hadrons, the first ones that appear are neutrons, protons, and electrons. And then when you start having these correlations with the different chemical potentials, you start having hyperons, okay? When you overcome at least the mass, okay, of this because of the chemical potentials, then you start populating and having fermions, okay? And then the equation of state gets softer, and then the mass of the object will be less, and then you have this hyperon puzzle. For kaons, you could think of similar things. You could think, of whether they appear or not. And again, the idea is to compare reactions in beta, reactions that are in beta equilibrium. So here is like, this is the one that I was mentioning all the time for the nucleon. So neutron going to a proton, electron, and antineutrino. And then you have this correlation between the chemical potentials. So if you only have neutrons and protons and electrons, you forget about hyperons, you will start having protons and electrons once this is fulfilled, okay? Now, kaons, you could think of a similar reaction where you have a neutron decaying into a proton and a K minus, okay? This would be a similar at this one. And of course, this is the relation between the chemical potentials, okay? So a neutron should be equal to the proton and the kaons, okay, fine. But I mean, the kaons are bosons, right? So actually, I'm talking about its mass, okay? Basically, the first order correction is its mass. So the idea here is this reaction energetically more favorable than this one in neutron stars? How this can be measured? So the idea, in order that this is energetically more favorable than this one, is that the chemical potential of the kaon, okay, at some point, it gets smaller than the chemical potential of the electron. Otherwise, this will also be more difficult than this one, okay? And you can see, I mean, the neutron proton mass, I mean in matter, I mean, this is change, okay? These chemical potentials are evolving with density, okay? So it's more difficult to have this reaction than this one at first stage, because if the chemical potential is the mass of the kaon is 500 MeV, okay? The mass of the electron is what? Half MeV, okay? But the neutron stars, the story is not that, the chemical potential of the electron actually is not given by its mass, okay? It's given by how it evolves with density, okay? And in a Fermi gas relativistic model, you can obtain evolution, okay, with this chemical potential. Of course, now you have neutrons and protons, so this is not the same reaction. But the idea here is whether this chemical potential of the kaon is smaller than the chemical potential of the electrons. And this means if at some certain density, the chemical potential of the electron gets equal to the chemical potential of the kaon. So if this happens, then you will start having kaons in your star. And since kaons are bosons, they will condensate. So it will create condensates. So because they are not fermions, so they don't have to populate a Fermi sea, they can stay in the same state, okay, in the ground state. And you can imagine that having a kaon condensate is different than having a hyperons in the medium, okay? So the question, of course, is this possible? And this is only possible if we lower enough, the chemical potential or its mass. So it means that the attraction that fills the kaon in the medium has to be strongly enough in order for this to happen. This is for K minuses. For K0, K bar, it's even more difficult because they are not charged particles. So basically the chemical potential has to be 0, okay, or smaller. And even for the K plus. So you can imagine that it's even more difficult to have these particles. So people concentrate on the K minuses, okay? And of course, the first thing, in the 80s, after, discussing the different possibilities in neutron stars, it was, thought, that the kaon condensation is irrelevant because the mass of the kaon is 1,000 times larger than the mass of the electron. And even if the chemical potential of the electron it changes with density, and you can get maybe to 200, 300 MeV, you really have to lower a lot the mass of the kaon. However, since talking about this, the chiral models or the chiral effective theory appeared, they realized there were some hints that it might happen, okay, that we might have this modification in mass of 200, 300 MeV. Even you have seen it in the phenomenological models when I was discussing chaonic atoms, right? They were discussing about attractions of 2 minus 200 MeV, okay? So then people start getting interested, okay, again in kaon condensation, and I'm talking at the end of last century. So they start analyzing this, basically this reaction here, okay, whether this was possible, okay? So you had your model where you had nucleons, so you knew how your chemical potentials were going with density, neutrons, protons, and electrons. You also had some description of the kaon mass or Lagrangian, chiral Lagrangian for the evolution of the kaons. And then you were analyzing whether this condition was being fulfilled or not, okay? And this is what it has been done here, for example, from a paper actually on the 95, from the same author that already said like 14 years ago that it was irrelevant, already, you know, start looking at this after these new ideas on chiral effective theory, okay? And this is the pressure versus the energy density, similar to what I show you for hyperons. This will be nucleons only. So, sorry, nucleons, protons, and electrons, okay, so in beta stable matter. And now if you start putting, you know, a condensate, then you will start having, you know, this change into the shape of the pressure versus energy density once they appear. Those different lines are due to different attraction at saturation density. So at some certain densities, you have this value, and you can see the larger the attraction is, the faster these kaons appear. And the effect, as you can see, you're moving from that line to that line, which means lower pressures for the same density. You have here at this energy density, now you have less pressure than the other one. So kaons were also softening the equation of state, okay? Because of this softening, now here is a radius versus mass. I was showing you before mass versus radius, but this plot somehow is different. So for this minus 120 MeV, I think it's the same paper, you see that the maximum mass, it's here, is around 1.5, as compared to almost 2 solar masses here, okay? So there is a softening of the equation of state, which translates into a reduction of the mass, okay? Of course, I mean, these models is from the 95, so we didn't have still measurements of 2 solar masses. So nowadays, you even will say without kaons, this is not working, this model, okay? But anyway, the effect is that, I mean, you have kaons, it softens, and you have less mass. So what happens now if you have hyperons? So hyperons make kaons, make it more difficult for kaons to appear. Why? You can see here, these are fractions that, as I was showing you before, for hyperons as a function of the density. This U is density. You have the different particles here. And now you can see here hyperons. And unless you know, this is different kinds of model, different strengths, okay? But you can see here that in those ones, there were kaons, but it was very difficult to have them. Only in this case, you know, it's being pushed, appears, but at really large densities. This is 3 times, 4 times saturation density, okay? Whether you have first hyperons, lambdas. What it means? It means, well, this is the hyperonization on kaon condensation. Basically, hyperons are making kaons more difficult to appear. How do you understand that? You have to understand that by hyperons, when they appear, remember I told you the equation of state gets softer. This means actually that the Fermi levels of the other particles are being lowered as well, of the nucleons and electrons, okay? Because you're not populating more nucleons. You are now populating hyperons, okay? So on one hand, there is a reduction on the Fermi momentum, okay, of the electrons. And on the other hand, there is, because now you have hyperons, so you don't need so much electrons anymore, okay? So you can see here how the electrons were rising, and when start appearing negative particles like sigma minuses or cascades, the electron fraction is reducing, okay? That means that the chemical potential of the electrons is being reduced. So if the chemical potential of the electrons is being reduced, and my condition was that at some point this is true, that the chemical potential of the electrons is larger than the chemical potential of the kaons. So if you're reducing this number, means that it's more difficult that this happens, okay? So this is what you're seeing here, that kaons, you know, appear, it's making more complicated for kaons to appear. Okay, this is from also from the end of the 90s. So since then, there has been a lot of work, some people working on that again. But now, of course, trying to fulfill this requirement of 2 solar masses, and also not only working on neutron stars, but on proto-neutron stars, so the origin of the neutron star, core collapse supernova, neutron star mergers, okay? Now people are also analyzing this kaon condensation in neutron star mergers. And now just an examples, okay, of models. Here are mass and radius, here are radius and mass. I don't know, people plot it in different ways. But just that you see that, for example, the effect of the kaons in this model, this is this dotted line here as compared to the green wall in their model. So there is this softening, this reduction in mass here as well. So here is with nucleons, and this is with kaons as well, the same model. In those cases, for example, on this, there were no hyperons already, so there is a softening as expected. Now with hyperons, there is also this softening together. We're talking about potentials of around minus 120 MeV, minus 140 MeV at saturation. And again, I mean, other kinds of more recent models, 2021, for example, having nucleons, hyperons, deltas, kaon condensates, and comparing with, you know, observations. Here are different observations of pulsars, of gravitational waves, and these are 3 different equations of state, where the green one contains delta, kaons, hyperons, and nucleons. And the black one, you can see here, is only nucleons, hyperons, and kaons, okay? But with a different, well, there are differences. So you can see that people have already, and are still working on the effect of the kaons, okay, inside neutron stars. But again, the potentials I'm talking at saturation only, not on larger densities. At larger densities, you can find the star that are even larger, okay? It is really deep, deep potentials. So again, this condition is the one that it has to be fulfilled. But this means that you need a lowering of the mass around 200, 300 MeV. This maybe, you know, this is the case, maybe it can happen. But if you go to the chiral Lagrangians, the ones that I was using also for Chaonic atoms, the attraction was even less. So from the point of view of unitarized schemes, kaon condensation seems very unlikely. Whether, you know, I'm showing you examples of other phenomenological models that might also get you to have kaons inside neutron stars. So actually, with that one, I'm finishing. So, well, here bibliography, I just put you a review that we did recently, but there's also other information you can find. And I mean, I hope at least with this lecture to have you, you know, become interested in strangeness with all these lectures in particular, because, you know, I'm discussing baryons and mesons with strangeness. And also that, you know, that you realize it's a hot topic. There is a lot of unknowns still from the theory and also from the experimental point of view. Things hopefully are improving in the next years with new experiments. And also the theory, you know, there has been a lot of improvement, especially since effective field theories, you know, were start being, you know, constructed and being used. And yeah, so if you have any questions, just feel free to, because we have like 15 minutes, well, maybe 10.
Thank you very much, Laura, for this nice review. So many results. There is an exciting time also in this field, apparently, which is very good.
Yeah, it is.
For all of us.
Sorry?
No questions.
No, I think people are
I
exhausted.
have a question.
You have a
Like,
question,
yeah.
okay.
Is it possible to have the same reaction that neutrons go to proton, but instead of kaon, we go to pion for a non-strange?
Yeah, people have also discussed pions, okay? But there's an issue here. The interaction of pions and nucleons, kaons and nucleons, I'm telling you, there is an attraction, okay? At least in the low end, what is in the S wave, in partial wave, but pion-nucleon interaction for low energies using, in S wave is repulsive. So as a first, approximation, if pions already have small repulsion, okay, then it seems more difficult for them to change its mass. So they are increasing their mass, okay? So they are making more difficult this reaction. However, this is not the whole story, because for larger energies, you also talk about P waves, and this becomes attractive, okay? So there is literature discussing pion condensation, okay, and the possibility. However, as I said, this is a bit more tricky because pion-nucleon interaction in S wave at low densities is repulsive. Okay, so you are going into the wrong direction. Okay.
Okay.
Yeah. Adriele, yes.
Could you possibly tell us something more about the elliptic flow, the first one, new one?
Yeah, the B1
in particular for strange.
Okay, I'm not an expert here. As you see, I went really fast on that. So I mean, the elliptic flow, the B1, B2 is kind of is an expansion, okay, on the observable, on the flow. So the B2 is the one that I know people all the time they had been looking at because of this telling you how matter flows. The B1, to be honest, people got interested, is this first expansion in this, I can give you some literature, but I don't know, the physical picture of what B1 means, I cannot tell you well, okay? So the B2 I understand better. So, okay. But yeah, and there is, depending on the attraction, there is a different behavior of this B1 and B2, okay, depending on attraction and repulsion. But okay, I can just maybe pointing you if you're interested in some reviews better than me explaining it.
Okay, thank you.
Other comments, questions? So also this measurements, this spectroscopy that you have addressed the first day, it seems very promising, no? To understand if it exists enough repulsive interaction
yes.
in the stars, no?
Yes.
And there, I think there will be definitely precise data, no, in the next years.
I think so. I mean, as far as I know, they are really concentrated on hyperons. On kaons, I don't think so. But yeah, so they are really, seems very interesting, results and really to have more scattering data that we are lacking of.
Yeah.
So.
Well, I'll say.
Hello.
Please.
Yeah, sure.
Yeah, I have another question. I think during the first lecture or something like that, you show a picture about the hypernuclei where
yes.
you show there are it's possible to put a lambda in many different nuclei, but
yes.
Is it possible to put a lambda in any nuclei, or there are some?
Okay, I know that they have been working on. I mean, I guess because of they are easier to be produced on the lightest ones. Okay, hydrogen, helium, lithium. So technically, I'm assuming that it must be easier, okay? But they have, even let me check. Let me I can share it with you again, the slide and the okay, let's choose here. I can share it. Wait a sec here. Okay, let's share. Okay. There was again. Here. So Aluminium, silicon. Okay, this I don't see. So I don't know, I guess it's more and more complicated as you have heavier. I don't know the how do you say, the limits, but at least onto aluminium, you know, we're here, we have some lambda.
Yeah,
So
on the graph on the slide before, I think
Yes.
it's go until 200 or something like that. No, I don't know which slide then.
sorry.
Yeah,
But this one.
Yeah.
Yeah, that's right. That's right. They go to 200. That's right. That's right. You're totally right. Yes. Yes. So it seems, yeah, it's feasible. Yeah. Yeah.
Okay.
I was guided. Yeah, I was guided by this, you know, and of course I don't see those ones here. But yeah. So it seems, yeah. So yeah, I was, you know, why I was thinking that, because I was looking also at the lambda here in beryllium, in helium and bohr, okay? And I don't see that they can have it too larger, maybe because it's more complicated, okay? But yeah, I would say, I mean, I can also check, you know, experimental articles, and maybe they say, you know, how difficult it is to get this.
Okay.
No, but also I think that if you have data for light nuclei, you can compare with calculations more easily, more efficiently. So you understand more now the interaction between
Yes.
lambda and proton and neutron.
Sure, definitely.
This
That's
is
true.
also a point.
Mhm.
Other questions? Well, I see that the number of connected participants is decreasing.
It's going, yes.
So I would not push too much this session any longer. If I don't see any other question booked, I would close it. Okay.
Very good.
Just 1 minute to thank Laura again and to thank all the lecturers, and above all the participants, in particular the ones who were still connected, I would say.
Especially on a Friday afternoon.
Friday afternoon at 6 p.m.
Yes.
And okay, unfortunately, I cannot say that in person, but I want to thank also the organizing committee
Yes.
and the DPI people. Alessio, Annalisa, Mauro, Matteo. You have not seen them, but they are very efficient. I talk to them every day, and they are very kind. And also, well, Elena Santo Pinto, the organizing committee, Elena Santo Pinto, Angelo Bonaccorso, Maria Colonna, Enrico Picezzi, Ignazio Mombaci, Andrea Beraulo, and Vincenzo Greco. And it has been, I think, for me, very, very instructive 2-week program. I hope also for you. And well, let's hope that next time it will be in person, as it must be. Thanks a lot. Anyone
Thank you to you,
want to
Sergio.
Okay. Muchas gracias, Laura. Vale. Very well. So see you next time somewhere.
Thank you. See you.
Bye.
Bye.